Hello students, good day. At long last, we are able to start some applications of the first derivative. And in today's lesson, we're going to look at the derivative as instantaneous rate of change. So at the very top of this document, it says, the derivative is the instantaneous rate of change of the dependent variable with respect to the independent variable. So if we have dy by dx, this is the instantaneous rate of change of y. Y here is the dependent variable with respect to x. X would be the independent variable. And the lesson today is going to focus on a special case, and this is rectilinear or straight line motion. And essentially, we're going to look at the relationship between displacement, velocity, and acceleration. Okay, our first relationship is here for instantaneous velocity. The velocity is ds by dt. The velocity is the instantaneous rate of change of the displacement with respect to time. So this means that if you take the first derivative of displacement with respect to time, you will be finding velocity. The second relationship is for instantaneous acceleration. Acceleration is equal to dv by dt. So the acceleration is the instantaneous rate of change of velocity with respect to time. This means that if you have a velocity equation and you take its derivative with respect to time, you will have the correct equation for acceleration. And if you put these two concepts here together, you'll get the third and final relationship, and that is that acceleration is the second derivative of displacement. I'm noticing here it's blurry, the printing. This says d squared s over dt squared. Okay, so again, it's the fact that if you're starting with displacement and you take its derivative once, you will have velocity. If you then take the derivative of velocity, you will have acceleration. So acceleration becomes the second derivative of displacement. And I've got five questions that we're going to go through together. Okay, in the first example, we have determine the velocity and acceleration for the displacement given by s equals s naught plus v naught t plus 1/2 at squared. Okay, so determine the velocity. Velocity is the first derivative of displacement with respect to time. So all I have to do is take the derivative of these three terms in the trinomial with respect to time. Notice that the first term doesn't contain the variable t and therefore is a constant. It's equal to the initial displacement. And so its derivative is equal to 0. Now we put in the plus sign. What would be the derivative of v naught times t? The derivative of v naught times t is v naught times 1, because the derivative of t is 1. Now we put in the plus sign, and we have the term 1/2 at squared. What is the derivative of 1/2 at squared? It is 1/2 a multiplied by 2t. The derivative of t squared is 2t. So we end up with v equals v naught plus at. Okay, so this term here simplifies after multiplying 2 by 1/2. So we get the velocity formula v naught plus at. Okay. Now we were going to find the acceleration. So the acceleration is the first derivative of velocity with respect to time. And that means, as I said, it is also the second derivative of displacement, okay, which is written this way. D squared s by dt squared. So all I have to do is differentiate these two terms now, again, with respect to time. The first term here does not have the variable t in it, so it is a constant. It's equal to the initial velocity. The derivative of that constant is 0. So we put in a plus sign. Now we take the derivative of a times t with respect to time. So this is just going to be a times 1, since the derivative of t is equal to 1. So we just have the acceleration is equal to the acceleration when we're done. Okay? All right, so that's our first example. And here's a second one. The distance in meters traveled by a subway train after the brakes are applied is given by S is 20t minus 2t squared. T is the time in seconds. How far does the train travel after the brakes are applied in coming to a stop? Okay, so we have the displacement equation. And essentially, if we knew how long it takes to come to a full stop, we could substitute it in here and we would have the answer to our question. We would know how far it travels in coming to a stop. However, at this point, we don't have a value to substitute for time. The key to this question is, when the subway train stops, its velocity will be equal to 0. Okay, so I'm going to write here, the train stops, or the train is stopped when the velocity is equal to 0. Okay, so now this gives us a way of solving for the time. If this is the displacement, we can write out the velocity function because we know it's the first derivative of the displacement function. So taking the derivative of this, the derivative of 20t will be 20 minus the derivative of 2t squared will be 2 times 2t, so it's 4t. Okay, the 2 comes forward, multiplies by the 2 here. 1 is subtracted from the exponent. So we now have this velocity expression. The train will be stopped when the velocity is 0. So that means when 20 minus 4t is 0. And certainly here you can see how to solve for time. Negative 4 times t will be negative 20. So we're just isolating t here. And t is negative 20 divided by negative 4. So t is 5. And this will be in seconds. So what have we determined? We've determined that once the brakes are applied, the train will still travel for 5 seconds. That's the stopping time. It's 5 seconds after the brakes are applied. So certainly now we can answer the question, how far does it travel in these 5 seconds? So all we have to do is evaluate now. So we'll say the distance after 5 seconds is given by, so we take this displacement equation and we simply substitute 5. Okay, so we're going to get 100 minus 50, in other words, 50 meters. And now our question is answered. Okay, so the train will travel 50 meters after the brakes are applied. Okay, let's move on to a third question. This question reads, the displacement in centimeters of a piston during each 6-second cycle is given by S is 6t minus t squared. In part A, we are asked, determine the time at which the velocity of the piston is 3 centimeters per second. Okay, so this would suggest that we begin by writing an expression for the velocity. The velocity is the first derivative of displacement with respect to time. So we have to take the derivative of 6t minus t squared. And this is 6 minus 2t. So part A says, when is this velocity equal to 3 centimeters per second? So we take 6 minus 2t, we set it equal to 3, and we will solve for t. Negative 2t is, now it'll be 3 minus 6, which is negative 3. So t is negative 3 divided by negative 2, which is 1.5 seconds. Okay, so at 1.5 seconds, the velocity is 3 centimeters per second. Part B, determine the acceleration of the piston. So the acceleration is simply the first derivative of the velocity. Here is our velocity expression. What is its derivative? It will be 0 minus 2 times 1. 0 minus 2 times 1, or negative 2. And don't forget to include appropriate units for acceleration. So in this case, it will be centimeters per square second. Centimeters per second squared. Okay, example 4. A bullet was fired straight upward so that the height in meters after t seconds was given by S is 600t minus 5t squared. Part A, determine the expression for the velocity of the bullet. So the velocity is the first derivative of displacement with respect to time. So we differentiate this binomial. We'll get 600 minus 10t. So that's part A solved. Okay, part B. What was the greatest height reached by the bullet? So the bullet, remember, is being fired straight upward. So at some point, it'll reach its maximum height. The key here is that it will then stop before making its descent. So we should state that we know that at its greatest height, it will be stopped. In other words, its velocity will be 0. So it'll be at its greatest height when its velocity is equal to 0. So we can take 600 minus 10t and set it equal to 0. That's our velocity equation. So 10t is 600. And therefore t is 60 seconds. Okay? So it'll be traveling for 60 seconds in order to get to its highest point. So now when we want to find the height after 60 seconds, we'll use our displacement equation. So we're going to now find the height at or after t equals 60 seconds. So that means we go to our displacement equation and we'll substitute 60. Okay, and if you put this into your calculator, you'll find that you get 18,000 meters as your answer. And that's fine to leave it like that, but we could also change it to 18 kilometers. All right, so the bullet travels upward for 60 seconds to get to its maximum height, and that maximum height is 18 kilometers. Okay, we'll do one last problem together. Problem 5 says, let SA equal 4t squared plus 5t plus 15, and SB is 2t squared plus 9t. These are position functions in meters of cars A and B that are moving along parallel straight lanes of a highway. Question A says, at what instant of time in seconds do the cars have the same velocity? So we have to start by finding a velocity expression for each car. And this is done by taking the first derivative with respect to time of each displacement equation. So we're going to take the derivative of SA. We're also going to take the derivative of SB. Okay, so the derivative of this trinomial will be 8t plus 5. And the derivative of this binomial is 4t plus 9. Now we have an expression for each velocity. The question says, when will these velocities be equal? So all we have to do is equate the two expressions. And again, solve for t. So this means collection of like terms like this. We will have 4t is 4. So at t equals 1 second, the cars have the same velocity. Part B, what is the velocity of each car at this instant? Well, the velocity of A will be 8 times 1 plus 5, which is 13, and units would be meters per second. And the velocity of B, 4 times 1 plus 9, which of course is also 13 meters per second. So we can see that indeed it is at 1 second that the cars have the same velocity. Part C, what is the acceleration of each car at this instant? So the acceleration of car A is the derivative of its velocity with respect to time. So here's the velocity of car A. We take its derivative with respect to time. And in fact, we will get 8. The appropriate unit, meters per second squared. So car A will be accelerating at 8 meters per second squared. What about car B? We'll take its derivative. We'll take the derivative. Oh, this says B here. How come this says B? Uh-oh, let me fix that for you guys. I gotta get my white out, which is far away. Sorry about that. I know I was saying A, but somehow I wrote down B. So sorry about that. Okay, so we took this equation and we differentiated with respect to time to get 8. This is for the acceleration of car A. Now we're working on the acceleration of car B. So we must use the velocity of car B and take its derivative with respect to time. Okay, so take a look at the equation, differentiate it, and you'll get 4 times 1 plus 0, or 4 meters per second squared. Okay, so at 1 second, the cars each have a velocity of 13 meters per second. However, one is accelerating at 8 meters per second squared, while the other is accelerating at 4 meters per second squared. Okay, so these are just a few examples which are utilizing the main relationship between acceleration, velocity, and displacement. The fact that if you take the derivative of displacement, you will have velocity. If you take the derivative of velocity, you will have acceleration. Those two facts combined, remember, also mean that if you start with displacement and take its second derivative, you will also have acceleration. Okay, and this is a special case, remember, of the fact that for any y and x that have a relationship, dy by dx is the instantaneous rate of change of y with respect to x. And we're going to be using this more general relationship in our next topic, which will be related rates problems. You can see that there are some recommended problems listed from your textbook. These are to practice today's relationship here for straight line motion. Okay, thanks a lot, class. Have a great day.